What's going on, you guys? So today we're doing min cost climbing stairs. And so the idea behind this one is we'll be given an array and we need to figure out, we need to pay. Well, let me read it for you guys. So on a staircase, the ith step has some non-negative cost of I, assigned, zero indexed. Once you pay the cost, you can either climb one or two steps. You need to find minimum cost to reach the top of the floor. And you can either start from the step with index 0 or with index 1. So let's do some examples. So let's see. We'll do 10, 15, 20. So we can start at 10 or 15. So if we start at 10, we can hop one or two steps. So we're probably going to hop okay, so if we start at 10, then what's our cost? Okay, so 10 plus, let's see, we go one step, that's 15, and then we can go two steps, so we only have to pay 25. Does it say that somewhere? Once you pay the cost, you can either climb one or two steps. Okay, so our goal is to get to one beyond, is to get outside of the array. So once we're at 15, we can go 1, 2 to reach the top. Or if we're at 20, we can just go to the top. So if we start at 10, our best case is do 10, 15. If we start at 15, we can go directly to the top. Yeah. So from 15, we can go 1, 2 to the top. So we're going to choose 15. Okay. Cheapest is start on cost 1, pay that cost, and go to the top. Okay. All right, now let's do this next one. Okay, and so for this one, what are we going to do? Let's see, so our goal should be to avoid, let's just do cost equals, our goal is to avoid these big hundreds. So we're going to start on 1, or on 0, obviously. So 1 plus, and then we're going to hop 2 steps to here. So plus 1. And we're going to skip this one and hop to this step. So plus 1. We're going to hop 2 steps, get here, plus 1. Okay, so we're here, and then we're going to take 1 step to get here. We're going to take 2 steps to get here. And we can hop off after paying that. So that is 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5. I think this is wrong. All right, so 1, 2, 3, 4, 5, 6. Okay, so I missed a 1 somewhere. Okay, so what's the recursive relationship? So let's do it this way. Let's say we're going to make an array. It's going to be the cheapest to get to that point. Let's just call it cheapest. And so cheapest 0 will be the cheapest way I can get to 0. Cheapest 1 will be the cheapest way I can get to 1. So what's the cheapest way to get to the top? We take the min between the last 2 entries of cheapest, right? So we can get to the top either from the last position or second to last position. So if we just calculate the minimum of these 2, then that'll give us the value for min cost climbing stairs. Okay, so how do we what's the cheapest to get to 0? 10. What's the cheapest to get to 1? 15. What's the cheapest way to get to 20? So we'll have to pay 20 at a minimum, and then we can look at, so to get to 20, we can go from either 15 or 10. So we'll take the min of the previous two positions. So previous 1 and previous 2, right? So that would be 20 plus the minimum of 10 or 15. So this is going to be 30. So I think we found our recurrence relationship there. So cheapest at position I, the cheapest way to get to position I is cost of I plus the min of the previous 2 of cheapest I minus 1. I minus 1. Cheapest I minus 2. Okay, so we add the current price plus the best way to get to it from either 1 previous or 2 previous. So that's how one relates to the next. And then we can get, so then the minimum of cheapest dot size minus 1 and cheapest dot size minus 2. So if we get the minimum of the last two positions, that'll give us the minimum for getting to the top of the stairs, right? So the top of the stairs is, we can get to the top either from the last position or second to last position. So if we take the minimum of those two, then we'll be able to find our solution. So let's code this up. Let's see. So let's deal with the base cases. So if this, if it's an empty array, or if it's null, turn 0. Or if cost at size equals 1, we'll just return that single value. Otherwise, we're going to return, what do we say, the minimum of, is that how we want to do it? So we can look at it from the end that way, or we can look at it from the beginning, right? Because we can start at either the first or the second step. So we could say, what's the cheapest? It's, wait, let's think. So this is a bottom-up approach. So let's come back to that for step 3. So we're going to do 3 steps, right? First step is going to be a top-down recursive approach. And then the third step will be bottom-up. So keep this in mind for bottom-up. But for top-down, let's start with, for top-down, we're going to say the minimum of min cost climbing stairs. Here, I'll show you here. Min cost. So if we take the minimum of, and we're going to call this, that's too long. So we're going to shorten this so it's easier to write. Climbing stairs. Let's call this min cost. So we're going to create another function to handle like the starting point. Okay, so what's our top-down recursive relationship? Yeah, this can be, we can use this as a top-down. Okay. Okay, so how can we use this? So just adding the function signature, we're going to return an int. So we're going to be incrementing. So we're going to be let's start off with what we're going to be computing here. We'll come back to that. So return, it's going to be the minimum of, so we can use, this is our relationship. So we're just translating this into code. So it's going to be cost of I plus the minimum of min cost I plus 1. Wait, is that right? Let me think. Min cost I plus 2. So let's think about step 0. So the cost of starting at step 0 is that price plus the minimum of either taking 1 or 2 steps. Yeah, I think that works. And so what are the limits on I? So I can't be greater than cost.size minus 1, right? That's the last value in the array. And if we do get that, we'll just return 0. Okay, so this should work. Let's see here. Well, it will work for small arrays like this, but it's not going to work for bigger ones. So let's try it for some small arrays. Right, because each call to min cost is going to create two additional calls. So this is going to be 2 to the n. This is O of 2 to the n. So top-down recursive is going to be O of 2 to the n, right? Because we make 2 recursive calls per value in the array. And it's going to be O to the 2n. So for each call, so the question is how many calls to min cost are we going to make? And therefore how big will the stack frame, stack call frame become? So each call to min cost causes 2 additional calls. And those all go on the stack frame, or on the call stack. So I'm getting 2n space complexity. Yeah, so this is not the most efficient. Okay, so how can we do better? So we're going to call min cost for the same I value multiple times. So we can just add memoization. So we only call min cost for each I once. So we'll do that with a hash map. And the idea is we'll check if the I value is in the map. If it is, we'll return it. Otherwise, we'll add it to the map and return the result. So if memo I does not equal null, we'll return memo I with our null check. So with the double exclamation point, we're guaranteeing that this value is not going to be null. And so we got a little cleaning up to do. We're going to make an intermediate result. We're going to set memo of I equal to it. And then we'll return result. And so this should work. So this is taking, so with memoization, time complexity, let's see. So still, we're doing better on space with the memoization. We're going to just over the end space complexity. Wait, let's think. What's the worst case space complexity? Yeah, we go to O to the n space complexity because we still have to call min cost for every value within cost. And those all go onto the stack. But now we won't have to do it multiple times. So we're doing a little bit better. We went from 2 to the n to we went from exponential to linear space complexity, so that's good. But time complexity, let's think. Time complexity is also better because once we get these duplicate calls, it'll just pull it from the memo, from the hash map. So we go down to O to n time complexity and O to n space complexity. Let's see if this doesn't hit a speed limit. Yeah, so that compiles, but we can still do better, right? So let's think about how we can do that. So we've been doing a top-down approach. Now let's think about a bottom-up approach. Okay. So for bottom-up, what are we going to do here? So we'll create a hash map. And it'll be a cheapest. We'll call it cheapest. We'll set cheapest of 0 equal to cost 0. And cheapest of 1 to cost of 1, right? Because we can choose at the beginning. We can choose to either start from 0 or 1. So that's the cheapest way to reach those 2 points. And then what do we do for the remaining values? So for I in 2 until cost that size, cheapest of I. That's what we need to figure out. How do we find the cheapest way to reach each individual point? Oh, this is where we can use this relationship here. Okay. So the cheapest at 2 is going to be the cost at 2 plus the minimum of reaching, plus the minimum cost of reaching that current value, right? So, for example, 20. It's going to be 20 plus the cheapest way to reach 20. And the cheapest way to reach 20 is either by taking 1 step from 15 or taking 2 steps from 10. So that's how we calculate each value from a bottom-up approach. And so in the end, we can just return the minimum of the last 2 steps, right? Because how do we reach the top? We either go from the last value of cheapest or the second to last value of cheapest. Okay, so let's convert this to Kotlin. Oh, and let's think about space and time complexity. So O of n time complexity and O of 1 space complexity, because we're getting rid of the recursive calls. Okay, cool. All right. Let's clean this up. And we can use, we don't have to use a map, we can just use an array. So memo 0. Should we call this cheapest? Yeah, it's a little bit clearer what it is. Cheapest 0 equals cost 0. Cheapest of 1 equals cost of 1 for I in 2 until cost.size. We'll say cheapest of I equals cost of I plus the minimum of the previous two values. Cheapest I minus 1, cheapest I minus 2. And then we'll return the min of the last two values, because we can reach the top from either of the last two values. Okay, let's see. Oh, we gotta allocate memory, so we'll do cost.size. Right. Oh, cheapest dot size minus 2. So that's the last value and second to last value. Okay, so that's a bit of an improvement on space there. And a little bit and better on time, it looks like. Interesting. And so there's one last optimization we can do. So let's take a look at what cheapest looks like as we're building it, and see if there's anything that sticks out to us. So let's use these examples, and let's build cheapest. So cheapest of 0 is going to be cost of 0. Cheapest of 1 is going to be cost of 1. And cheapest of 2 is going to be 20 plus the minimum of the previous two values. So 10. So 30. Okay. So it looks like we're only using the previous two values. So maybe we don't need to store everything in an array, in the cheapest array, or map, whichever you chose to use. Okay, let's do it for this one. Cheapest of 0 is 1, cheapest of 1 is 1, cheapest of 2 is 1 plus the minimum of the previous two. So 1, so 2. Okay, next one is current value plus minimum of the previous two, which is 2. So 1 plus 2 is 3. Current value plus the minimum of the previous two is 1 plus 2, so that's 3. So current value plus minimum of the previous two is 3, so 103. 1 plus minimum of previous two is 4. 1 plus minimum of previous two is 5. 100 plus minimum of previous two, 104. 1 plus minimum of previous two is 6. And then we take the minimum of the last two values. So it's going to be 6. So you notice here that we're only using the previous two values in order to calculate the next value. So we don't need to store everything in a cheapest array. We can just store the previous two values. So that's the last optimization, and it'll make it a little bit faster. It's still going to be O to the n because we have to touch each value of cost, but it should be a little bit less space. Okay. So we'll delete that. We'll call this var previous 2, right? So we're going to start off at 2. So 2 behind, 2 back is cost 0. We're going to, and 1 back is cost 1. So previous 1 is 1 back, previous 2 is 2 back. Okay. So we can compute the new value. So we'll say var new is going to be the same way. Wait. We don't need to delete all this. So our new value is going to be the current value plus the minimum of previous 1 and previous 2, right? So the minimum of 1 back and the minimum of 2 back. So that's our new value. So previous 1 back, when we increment I, so here's previous 1, previous 2. So here's I, here's previous 1, and then here's previous 2. So we're going to shift all those up 1. So previous 1 will become previous 2. So we'll set previous 2 equal to previous 1. And previous 1 will be the new value we've created. So we're just shifting those values each time through the loop. And then we're going to return the minimum of just the previous two values, right? Previous 1 and previous 2. Uh-oh. New. Oh. Fix that error. Okay, there you go, guys. So we've a little bit of a saving there. So O of 1 space, O of n time for this optimized bottom-up approach to min cost climbing stairs. All right, I'll see you in the next one.